Hello everyone, this is Chandrashekhar welcoming you all to the Sunday Ka Funda series. In this series, today we are going to practically demonstrate the capillary action through the tissue paper, how the water rises to the in the tissue paper using the concept of capillary action. So guys, I have taken three containers and I have intentionally taken different liquids, or it is actually water but colored water, different colored water in these three containers, so that it will be easier for you to distinguish between the three containers. All right, so I am having this tissue paper and I will put tissue paper, one tissue paper in the red water container and another one in the blue water container. So you can observe the effect of capillary action. You can see, do you see the water is actually rising through the tissue paper because the adhesion between water molecules and the tissue paper molecules is more compared to the cohesion between water and water molecules. All right, so guys, this will be going to take a little more time, but you can see there is a liquid rising and it is going to enter into the second or into the middle container. So after 5 minutes, as you can see, the liquid from the two containers is rising through the tissue paper and going to mix in the middle container. So guys, let us discuss the practical aspect or the practical or technical aspect, technical aspect of this capillary action. Thank you. Hello everyone, this is Chandrashekhar welcoming you back to the Sunday Ka Funda. So in this session, we will be discussing the technical aspect of capillary action. We have already seen the experimental demonstration. Now we will talk about the mathematics behind it. All right. So there are two types of intermolecular forces. One is force of cohesion, that is taking place between the similar molecules, and another is force of adhesion, which acts between the dissimilar molecules. All right. So when cohesion is weak, when cohesion is less, then the liquid will wet the surface. The liquid will wet the surface. The liquid will be called as wetting liquid. When cohesive force for the liquid is lesser compared to the adhesive force between the liquid and the surface, then that liquid will wet the surface, and that is why the liquid will be wetting liquid. And when the adhesion is, or when cohesion is strong, adhesion is weak between the surface. When adhesion is weak between the surface and the liquid, then the liquid will not wet the surface. It is called as non-wetting liquid. So by using this concept, whether cohesion is weak or the adhesion is weak, depending on that, if we put a glass tube, in the water, glass tube in a container of water, then what will happen? Water will rise in the glass tube. Why will water will rise in the glass tube? Because the cohesion between water and water is less compared to the adhesion between water and glass. That is why the water will wet the glass surface and water will rise to the glass surface, and the meniscus will be concave. It is concave meniscus. All right. This is how the water will rise. But if we put the glass tube in a container filled with mercury, then to our surprise, the level will fall. The level will fall. Why? Because the cohesion between mercury and mercury is strong compared to the adhesion between mercury and glass. So the mercury does not wet the glass surface, and the level of mercury goes down when comes in contact with the glass surface. It is non-wetting liquid for the glass surface, and the meniscus will be convex. All right. So how much the rise or the fall will take place, how to determine that?
we can talk about the rise or fall. Now let us say this is the free surface and there is a fluid rising H, or there is a free surface and the fluid falling is H. So how to find out the value of H? Let us talk about that. So this is the point P. The pressure at P is equal to, we can say pressure at P is equal to rho GH plus PATM, sorry, PATM minus rho GH. So we can say pressure here will be PATM if we are moving in upward direction. So the value of P here, P will be equal to PATM minus rho GH, isn't it? And outside pressure is PATM. So the force exerted will be delta P into pi by 4 d square. The force, upward force exerted, will it be upward or downward? There will be a downward force exerted. There will be a downward force exerted on the surface. On this surface, the downward force exerted is delta P into pi by 4 d square. And because of surface tension, there is a force developed, that is sigma into pi d. When the fluid rises, then the concave meniscus will be concave and the contact angle theta will be less than 90 degree. Here theta is the contact angle. Theta is the contact angle. So this is how the situation will be. Now if I talk about this P, the value of P is equal to PATM plus rho GH. So pressure is more, here the pressure is PATM. So the force will be upward, delta P into pi by 4 d square will be the force exerted, pressure force, and there is a convex meniscus, so surface tension force sigma into pi d will be acting like this, and this angle is theta, which is greater than 90 degree. Here theta is less than 90 degree. So the fluid will rise up to the point where the net force on the fluid becomes 0. So if we talk about equilibrium condition, net force must be equal to 0. So delta P into pi by 4 d square is equal to sigma into pi d into cos theta. Do you agree? And what is delta P? That is rho GH into pi by 4 d square. So this pi and pi getting cancelled out, d is d getting cancelled out with this d. So the rho GH into, it will be rho GH into d by 4 is equal to sigma into cos theta. So we can find out H. So H will be equal to 4 sigma cos theta upon rho into G into D. That will be the rise or fall of the liquid in a tube kept in it. All right. Now for rise, if the fluid rises, then theta will be less than 90 degree. If theta is less than 90 degree, then cos theta will be positive. If theta is less than 90 degree, then it is first quadrant, cos theta will be positive. And if cos theta will be positive, H will be positive. If H is positive, then there is a capillary rise. So theta will decide whether it will rise or fall. So when theta is less than 90 degree, which is the contact angle, or if it is concave meniscus, like this, if it is a concave meniscus, then there will be a rise of the liquid in the tube. And if theta is greater than 90 degree, like this is the contact angle, then cos theta will be equal to negative and H will come out to be negative. If the H will come out to be negative, then there will be capillary fall. So the formula will remain same, 4 sigma cos theta by rho GD, but whether it is capillary rise or capillary fall will be decided by the relative magnitudes of cohesion and adhesion. And that will decide the contact angle, right? So what is the formula we have discussed? H is equal to 4 sigma cos theta upon rho into G into D. That is the formula to be used, whether it is capillary rise or capillary fall. If it is a capillary rise, then H will be positive. But do you understand? H is inversely proportional to diameter. So more is the diameter of the capillary tube, then less will be the rise. This is H1. And this is, let us say, D2, this is H2. And this is D3, then this will be H3. So more will be the diameter, less will be the rise or fall of the liquid in capillary tube. All right. So there is a question. I want to ask you a question. Sorry. I want to ask you a question. If we put a hole, here, then what will happen? Will the fluid continuously come out? Will the water continuously come out, or will it become a fountain? And there are so many practical examples, more such practical examples where you can easily find out the capillary action, like the nib of a pen. Water rises to the top of tall trees because of capillary action. The oil rises in the cotton cord. You can always find in the morning the droplets on the leaves because of the capillarity, or because here we can say cohesion is more than the adhesion. That is why they do not wet. The water does not wet the leaf surface, or when the tissue paper is dipped in the glass of water, the water start rising in the tissue paper. These are some of the examples of capillary action. For more such sessions, please do subscribe our BYJU'S YouTube channel and stay in touch. Thank you and take care.